You know, there's this constant chemical balancing act happening all around us and even inside of us, all the time. It's this fundamental push and pull between two really powerful opposites, acids and bases. So let's pull back the curtain on this hidden world.
To really get this, let's start with a feeling I'm sure you've had, heartburn. That awful burning feeling in your chest. What is actually going on in there from a chemical point of view?
Well, the problem is pretty simple. There's too much acid. And the solution, hiding in a plain old antacid tablet, is its exact chemical opposite, a base. That little tablet kicks off an incredible reaction that brings relief, and it perfectly sets the stage for everything we're about to explore.
So before we can really appreciate the solution, we've got to understand the problem. And that means looking at that powerful acid just churning away inside your stomach. Your stomach is basically an amazing chemical factory. Its number one tool is hydrochloric acid, a seriously strong acid that's absolutely essential for breaking down your food. But you know, sometimes the factory goes into overdrive and just produces way too much. And that's when you feel that all too familiar burn.
Okay, so what makes an acid an acid? Chemically, it all comes down to the hydrogen ion, or H+. When you put an acid in water, it just starts releasing these ions. The more H+ ions it lets loose, the stronger the acid. And this little guy is the villain in our heartburn story.
Right, so every villain needs a hero, or at least an equal and opposite force. So let's meet the other key player in this whole chemical drama, the base.
I mean, just look at how perfectly opposite these two are. Think about it. The sour taste of a lemon, that's an acid. Now think about the bitter taste and that kind of slippery feel of soap. That's a base. Even the way they behave is different. Acids eat away at metals, while bases, they generally don't. They really are true chemical opposites.
And just like acids are defined by releasing hydrogen ions, well, bases have their own signature move. When a base dissolves in water, it releases hydroxide ions, or OH-. And this is the chemical that's about to go head-to-head with the H+ from the acid.
So this brings us to the main event, right? The climax of our story, the neutralization reaction. This is where these two opposites finally meet.
It's the classic showdown. You've got all this extra hydrochloric acid sloshing around in your stomach, and then you introduce a base from an antacid tablet. What do you think happens when they finally collide? Well, a reaction called neutralization happens, and you can think of it like a dance where everybody switches partners. The hydrogen, the H+ from the acid, finds the hydroxide, the OH- from the base, and they pair up. And what do they make? H, O. You know it as H2O, water. The ions that are left over then get together to form a salt. And what's the result of this epic battle? The powerful acid and the strong base completely cancel each other out, and they produce two of the most common, harmless things on the planet, water and a salt. By the way, in chemistry, a salt isn't just the stuff you put on your fries. It's the general name for the compound that's made in this reaction. The fiery problem is totally solved.
This whole idea of neutralization is such a huge deal that scientists came up with a way to measure it, to basically map out the entire acidic and basic world.
It's called the pH scale. The P actually stands for power, so it's literally the power of hydrogen. It's a scale that measures the concentration of those H+ ions we were just talking about. The more H+ ions you have, the more acidic it is, and the lower the pH number.
So here it is, the pH scale, and it runs from 0 to 14. Way down at the low end, you've got super acidic stuff like battery acid and stomach acid. Way up at the top, you'll find powerful bases like drain cleaner. And right there in the middle, at a perfect 7, that's pure water, totally neutral.
But here is the absolute key, the thing you have to remember. The pH scale isn't like a simple ruler. It's logarithmic. And that means each whole number step is a 10 times change in power.
Let me put that into perspective for you, because this is wild. Something with a pH of 4 is 10 times more acidic than something with a pH of 5, which means a solution with a pH of 3 is 100 times more acidic than that one with a pH of 5. It's a huge leap in chemical power for just a small jump in the number.
Okay, so we have this powerful scale, but how do we actually use it? How do we measure the pH of something and make this invisible property, visible?
And here's the challenge. If you have a beaker of hydrochloric acid and a beaker of a base, they probably both just look like water. They're colorless. And you definitely don't want to use your sense of taste or touch to figure it out. So how do we know what we're looking at?
Well, the simplest tool is good old litmus paper. It's a type of indicator, a special chemical that changes color when an acid or a base is around. You dip blue litmus paper into a solution and it turns red, boom, you've got an acid. Dip red litmus paper in and it turns blue, it's a base. It's a super quick, easy yes or no test.
But if you need more precision, you're going to use pH paper. This stuff is soaked in what's called a universal indicator, and it creates a whole rainbow of colors. You just dip the strip in, match the color to a chart, and you can pinpoint the exact pH value. Pretty cool, right?
All right, so let's boil this all down. What are the big takeaways? First, acids and bases are chemical opposites. One releases H+ ions, the other releases OH- ions. Second, when they meet, they neutralize each other, making harmless salt and water. And finally, we measure their strength on that powerful logarithmic pH scale, where every number is a 10 times leap in power.
From the acid in that lemon on your counter to the base in your soap, this chemical balancing act is happening everywhere, all the time. It's a fundamental process that shapes our bodies and our world. So the next time you see these everyday things, just think about the invisible chemical dance that's going on. What other reactions are out there, hiding in plain sight?